Okay, for these extra practice problems, I am going to help set up the equations, but I'm not going to solve them. You can practice that on your own. Okay, so an economy has four sectors: mining, lumber, energy, and transportation. The key to this kind of problem is to remember that production equals consumption for every sector. So I've got mining, lumber, energy, and transportation. So this is production for each of these. Production for mining has to equal the consumption for mining. So mining produces some amount of stuff that we're going to call it M, and it has to consume an equal amount of stuff. We'll measure all this stuff units is going to be in dollars. Okay, so mining creates a certain amount of stuff, M. It needs to consume the same amount of stuff. So it consumes 20% of what it produces. So it produces some amount of stuff. It sells 10% of it to lumber and 70% to energy and retains the remaining 20%. So it's going to consume that 20% of what it produced. Okay, and then we have to see how much of lumber, energy, and transportation it consumes. So lumber sells 15% of its output to mining. So it consumes 0.15 of lumber's production. And then I'm going to move to the next sentence. Energy sells 10% of its output to mining. So mining consumes 10% of energy's production. And then let's see, one more. Transportation sells 15% of its output to mining. So plus 0.15 of transportation's production. All right, then we go through and go read each sentence again to figure out the consumption that lumber has. Okay, so mining sells 10% of its output to lumber. So lumber consumes 10% of the mining production. And then lumber sells 15% to mining, 50% to energy, 25% to transportation, and retains the rest. So lumber retains the rest after 15 and 50 is 65, plus 25 is 90, leaving 10% for lumber to consume. And then energy sells 10% to mining, 20% to lumber. So 20% of energy's production goes to lumber's consumption. And then finally, transportation sells 15% of its production to lumber. So plus 0.15 transportation. Energy. So I go back to the first sentence and reread, right? Mining sells 10% of its output to lumber, 70% to energy. So 0.7 of mining's output goes to energy. Okay, lumber, 50% goes to energy. And energy, it sells 10 to mining, 20 to lumber, so that's 30, 30 to transportation, that's 60, and retains the rest, so 40% of its own production is consumed by energy. And then lastly, transportation, it sells 60% to energy. Okay, transportation. Mining doesn't give anything to transportation. Okay. Lumber is 25% to transportation. Energy, 30% goes to transportation. And transportation, 15 and 15 is 30, and 60 is 90. So it keeps 10% of its own production. Oops. Just realized that should be a T. Okay, so that is the setup. At this point, you need to move all of the variables to one side so that you have only constants on one side, and then you'll set up an augmented matrix. So like I would subtract M from both sides here, subtract L, subtract E, and subtract T. So your new equations will be 0.2 minus 1 is negative 0.8 M plus 0.15 L. And then my next equation would be 0 equals 0.1 M. 0.1 minus 1 is negative 0.9. Etc. Okay, you guys can finish that on your own. Okay, to balance this chemical equation, I'm going to set up a vector equation where each vector holds an element from these molecules. So I've got H's, O's, CA's, C's, and that's it. Okay. So each vector is going to hold the number of elements H, O, Ca, and C. And then what I'm really looking for is what coefficients do I put in front of each of these to make this balance. Okay, so my first molecule, H3O, so how many H's are in H3O? 3. How many O's? 1. 0 CA's and 0 C's. Times X1 plus CaCO3, 0 H's, 3 O's, 1 Ca, and 1 C. And then this becomes an equal sign. My next molecule is H2O, so I have 2 H's, 1 O, 0 CA's, 0 C's. Okay, Ca is just the single element, so 0, 0, 1, 0, X4, plus, finally, last molecule, CO2, so I have 0 H's, 2 O's, 0 CA's, and 1 C. Now I have a vector equation. I'm just going to translate it to an augmented matrix, row reduce, and solve. One thing that is tricky is that you do have to move all the unknowns to the same side of the equation. So when I make my augmented matrix, I'm going to start by just putting in the column vector, the vectors as the columns of the matrix. But then these three that are on the other side of the equation, you have to move them to the left side, so the signs are all going to change. And what's going to be left when you move them over is 0, 0, 0, 0. So you would just row reduce that and solve. In a certain region, about 5% of a city's population moves to the surrounding suburbs each year, and about 4% of the suburban population moves to the city. And then we've got the 2010 populations in the city and the suburbs. So set up a migration matrix, use it to estimate the populations in the city and in the suburbs in 2012. Okay, so my migration matrix, I always have from and to, and then I'm going from the city and the suburbs to the city and the suburbs. So when you go across and down, you always want to go the same order, C, S, C, S. Okay, so from the city to the city, let's see. In a certain region, about 5% of a city's population moves to the suburbs. So city to suburbs is 0.05. And then about 4% of the suburban population moves into the city. So suburban to city is 4%. Everybody else stays where they are. So city to suburbs is 5%. That means city to city is 95%. And if suburbs to city is 4%, then suburbs to suburbs is 96%. So that's the migration matrix. And then to figure out the population in 2011, you're going to take your migration matrix and multiply by the state vector from 2010, which was 10,250,000 and 700,000. Okay, so this would be the give you the populations in 2011, and then to do 2012, you take your migration matrix and multiply by the result that you got for 2011. Plug that in here, and you'll get a vector that will be your answer. Okay, so this last one is a network flow. Each intersection builds us an equation. So I'm going to have 4 equations from the 4 intersections, and then there'll be a 5th equation for overall in and overall out. So let's look at intersection A. So cars or whatever is flowing in and out of these. Oh yeah, this is cars. Okay. So cars flowing in is 200 and 400. And that has to equal cars flowing out, which is x1 plus x4. Intersection B, cars flowing in is x1 plus x2. Cars flowing out is 700 plus x5. Intersection C, cars flowing in is x3 plus x4, and cars flowing out is 300. And intersection D, in is 600 plus 100, and out is x2 plus x3. And then overall, cars flowing in, we have 200, 400, this is going in, this is going in, this is going in, this is going in. Okay, that's all the ins. That has to equal the sum of all the outs. So let's see what's going out. 700 is going out. X5, 300, and that's it. So that's 5 equations with 5 unknowns. You should be able to solve it using the matrix methods we've been learning so far.